Yeah, I mean, I think the first thing I would say is that this needs to be understood before we get excited about any 7 sigma discrepancy with the standard model, which is this the green line.
The distance between the green and the result here. We should probably understand why there's a difference between these 4 and this one before we get excited about this distance here from the blue to the green. What's up, you scholars of enlightenment? I hope you're having a wonderful day and have a wonderful Easter weekend planned. Physicists at Fermilab have just released a painstaking analysis of CDF2 experimental data that suggests that the mass of a fundamental subatomic particle of nature, the W boson, is slightly more massive than we would expect it to be, given the predictions of the standard model of particle physics and past experimental data. The result is the most precise measurement of the W boson mass ever produced, and is more precise than all previous measurements combined. Although the discrepancy between the W boson's predicted mass and this new measurement is tiny in absolute terms, it is incredibly statistically significant and represents the first conclusive experimental result that is at odds with the standard model. However, the result is in strong tension with measurements from other experiments such as ATLAS and LHCb at CERN, and came as a shock even to the Fermilab scientists themselves. The international particle physics community is now considering, debating, and checking the result. If the result is accurate, the implications for fundamental physics are enormous. Cracks in the standard model will help scientists to pinpoint where to look for new physics and potentially lead us to explanations for unknown phenomena such as dark matter, dark energy, and even the origins of the universe itself. To help us dig more into this measurement, how it was made, its potential implications, and the road ahead, we welcome another fantastic special guest, Dr. Mika Vesterinen. Dr. Vesterinen is an experimental particle physicist using data from the LHCb experiment at CERN to understand quark flavor and electroweak symmetry breaking. And his thesis was an analysis of data from the D0 experiment at the Fermilab Tevatron. So who better to help us understand exactly what's going on over at the Tevatron? So, Mika, the first question that comes to mind, we've got this new blockbuster measurement from CDF of the mass of the W boson. Now, there'll be a lot of people out there who are watching who aren't particle physicists, who might not know what the W boson is. Why is this such an important particle in our everyday lives? Why do we care so much about W bosons?
Yeah, so the W boson is one of the fundamental particles of the standard model. So the standard model has 2 top level types of particles, the fermions, which are the matter particles, and the bosons, which are the force carrying particles. And the W boson is one of these. And broadly, these bosons map to the 4 fundamental forces of nature. So the starting with the strongest force, the strong nuclear force is mediated by the gluon, and then electromagnetism is mediated by the photon, and then the W boson and the closely related Z boson mediates the weak nuclear force. And now you might ask where I said there are four forces. So gravity we don't talk about because that's we don't actually have a quantum theory of gravity. So probably the photon is the force carrier that sort of we feel most in our everyday lives. It's sort of, that's electromagnetism holds together atoms and so on. The weak nuclear force mediated by the W and Z boson is important though, so the W boson is what mediates radioactive decays or the fusion that powers the burning of the sun and so on.
Yes. So when we're talking about changing one particle into another, what we call changing flavor, we're interested in W boson. So nuclear decay, fusion in the sun, for example, very, very important. So we want to know about the W boson. So that raises the sort of next question is, why do we care so much about the mass of the W boson? So this new measurement came out from CDF, and they seem to be saying that the W boson is slightly heavier than we might expect, significantly heavier in terms of statistics, but only slightly heavier in terms of absolute terms. Why are we so bothered, and why is this such a big deal in particle physics that we have this small discrepancy between what we expect from the standard model and what CDF, the experiment, is observing? Because a lot of people will look at it and say, well, this is only a small change in mass. Does it really make much of a difference?
Well, actually, the figure that you have now, to answer that, that figure is somewhat underselling the power of the standard model, because it appears that we have these four distinct gauge bosons, the blue slices of the dartboard, and the Higgs in the middle. And as we know, a simpler model or a simpler explanation of a phenomenon is more predictable and more testable. Well, actually, in the standard model, the photon, the W, and the Z are actually they're all actually very closely linked, and in fact, they're all very closely linked to the Higgs. But in some sense, we have this electroweak theory that combines electromagnetism and the weak force, and that combination also involves the Higgs. So actually, the photon, the W and Z, are actually somehow different mixtures of the same. They're actually different mixtures of something even more fundamental, which is the underlying gauge boson fields in quantum field theory. But the mass of the W boson and the Z boson essentially comes from the energy that's left over in the Higgs field that permeates the entire universe. So in these formulae, it's this V, so these formulae show very nicely how the W and Z boson masses are really have very simple predictions. They basically just depend on this energy of the Higgs field and the strength with which they couple to that energy of the Higgs field, which is these two different types of G's, the couplings. So if you can find another way to determine those V's and G's, you can predict the W mass. And if you can predict the W mass and measure it, then you're really testing whether this is actually whether that's correct, and the W really does get its mass from just its interaction with the Higgs field or something else.
So it seems like the mass of the W from what I sort of remember from back in my particle physics days, and also from sort of doing a little bit of research around this, essentially, if the W boson mass is way off, it feeds into other results, doesn't it? So if one of these mixtures, one of these values is slightly off, that has a knock-on effect in the whole electroweak sector. The sort of overall global fit doesn't kind of work anymore. Other things sort of start to be out of range, and it makes a knock-on effect in the whole sector.
Yeah, I mean, if we measure a W mass that's different from the one that's predicted, that we shouldn't necessarily think that means that there's something affecting the W, the mass of the W, and nothing else.
Yeah,
there's something that's all of these things are coupled together.
Yeah.
The mass of the W, the mass of the Z, the energy of the Higgs field, the couplings, they're all tied together. So somehow in the way that we fix some of the parameters and then predict the W mass, somewhere in there, there would be some other dynamics at play.
Yeah. Yeah. So if one thing is so if we go back to this one, we can get, for example, that the ratio between the masses is just going to be dependent on the coupling constant. So maybe there's a problem in the coupling constants, or maybe there's a problem somewhere else we know that there's something in our understanding of nature must be wrong if the W boson mass is off by a certain amount. Is that fair?
Yeah, I think so. It's somehow in the way that there's no measurement that you can do that just trivially gives you V or G prime.
Yeah.
There are you measure the cross sections of scattering different particles off each other. You did measure the decay widths of particles. You measure the masses of particles, and these, when you put these all together, you can sort of piece together what these depend on different combinations of these parameters, and you piece it together. So if if the CDF result is correct, then it means that that there would be some other dynamics that's sort of breaking that overall coupling.
Makes sense. So getting into the specifics of the work done at Fermilab, because I think you did your PhD based on some data from D0, didn't you, at Fermilab? Is that correct?
Yeah, so D0 was the competing experiment with CDF. So yeah, I did my PhD between 2008 and 2011. So I was actually working on studying Z boson production, and later on in studying simultaneous production of pairs of Zs and Ws and Zs.
Sadly, no result on this follow-up result on this coming from D0, is it? Because I think we chatted when we chatted to Dave Toback last week. He said they'd worn out their inner detector or something similar. So there's not going to be a W boson mass measurement coming from D0, unfortunately, or at least a follow-up.
I'm not sure if there's an officially approved D0 collaboration statement on this, but I think indeed I don't think we should count on an update from D0. Fortunately, D0 had actually already their last measurement was based on half of the data set, whereas CDF have up till 2 weeks ago had only measured about or had analysed about a fifth of their data set.
Yeah. Makes sense. So, like we said, going into that experiment. So, obviously, if we want to study W bosons and determine their mass, we obviously have to produce them. So, how do they go about producing these W bosons at the Tevatron and at Fermilab? What's the sort of process that's going on there for people to understand?
Yeah. So the collider is both the Tevatron and the LHC collider. They're high energy hadron colliders, and they're very similar in that sense to the CERN SPS collider that first discovered the W and Z bosons. The only difference is energies and whether you're colliding protons and antiprotons or protons and protons. So at the Tevatron, the Tevatron is colliding protons and antiprotons at a center of mass energy of just under 2 TeV.
Yeah.
And at that energy, it makes sense to collide protons and antiprotons because what you really want is the scattering or annihilation of quarks and antiquarks to produce things like Ws and Zs and other exciting things. And so the antiprotons have contain 3 valence antiquarks. The basic process is that the protons, which contain 3 valence quarks or antiquarks in the antiproton case, collide to 1 antiquark from the normally from the antiproton and 1 quark from the proton, annihilate together and produce a W boson, and that can decay in 9 different ways, and a few of which are used in the mass measurements.
So we can see sort of in this diagram the proton and the antiproton sort of come together. They smash together in this collider. The quarks that are inside and the antiquarks that are inside this proton and antiproton, they annihilate with one another. They produce this W boson. So E equals mc squared. You have a hell of a lot of energy. You smash these together, you can create one of these heavier W bosons, and then this flies off into your detector. Now, as kind of Mika said, it doesn't really hang around very long, and it decays down to, I think the decay that they look at in the CDF measurement is W to essentially an electron and an electron neutrino, or a muon and a muon neutrino. And then I guess we can see these tracks in our detector, and we can project back to know that that W was there. Is that fair?
Yeah, exactly. The only other additional, they actually use W decays to muons as well as electrons, so they get twice the signal.
Exactly, twice the bang for your buck. So what they'll see is essentially you smash these protons together, you don't detectors, but it decays into this electron and a neutrino. Now, you don't see the neutrino because it sort of just punches through your detector without being seen, but you see this sort of isolated electron track, and you can sort of trigger and keep these particular events. So how do we sort of a little bit more technical, Mika? How do we sort of trigger on these events? Are we just looking for a high energy, high transverse momentum isolated electron, and then some missing energy or missing momentum going the other way to show that there might have been a neutrino there? How are we isolating these events that are definitely W decays?
Yeah, so if you look for most of the proton antiproton collisions just have actually just involve the strong nuclear interaction, because it's the strongest force, of course, and that just produces more particles that couple to that force, so quarks and gluons. So essentially, in your figure, just more of these cyan,
these messy jets.
Yeah, these things called jets. Now, several orders of magnitude lower in rate, you get W boson production.
Yeah.
But fortunately, these are quite distinct from this this large background of producing jets, because of this single very high energy electron or muon, which tends to be isolated from other things. So that means in your final analysis, the level of background is relatively low. I mean, it's still a hugely important detail, but it's it's relatively low. And also, now I have to remember, because it's been 10 years since I worked on this collider. the tevatron was colliding. So the LHC collides at 30 megahertz. I think the tevatron is more like 1 megahertz or something like that. But that's producing a hell of a lot of data, and so most of the collisions have to be thrown away immediately.
Yeah.
But this single, the red track in your event gives you a signature that you can see very quickly and say, yes, we'll keep that event. So that's what we call triggering.
So is there any benefit, Mika, to the way that CDF and the tevatron is set up, which allows it to do this measurement more easily, and therefore why they've got a result on this out quicker, or is it just a temporal thing that they were working on it beforehand? Because it seems like naively you would think higher energy, higher luminosity at the LHC gives you more statistics. We can do this analysis quicker. However, if the collisions are messier, or there's additional systematics that are brought in by higher energy, I think it changes, for example, the parton distribution functions and such, which we might get into in a little bit. Are there benefits to using the tevatron and CDF for this measurement over the LHC?
Yeah, so there are definite advantages of the tevatron collider, but on the timescales of producing the results, I think it's fair to say that the CDF collaboration, this analysis may have taken 10 years since the data were collected. reflects how difficult it is.
Yeah.
But that was already after 10 years of practice on analysing the smaller subsets of the data as they were collecting it. So they were already, by 2012, I think was their last publication, they already really knew how to measure the W mass. So the Tevatron is a lower energy collider, and it's also a anti-proton collider, whereas the LHC is higher energy and has proton-proton collisions. Probably the most relevant difference is the higher energy, because what makes the W boson mass measurement so difficult is that you have W bosons that are so at the Tevatron even you have 2 TeV collisions, but you only need about 100 GeV, like 20 times less, to produce a W. So where does all the rest of the energy go? Well, some of it goes in, so it goes into your sort of P bar fragment jets, either the rest of the protons and antiprotons colliding, but a lot of it goes into the energy of the W itself. So that makes the measurement more difficult. But also at the Tevatron, it's more obvious that so you need a quark and an anti-quark to annihilate to produce a W. It's more obvious that the quark must come from the proton and the anti-quark must come from the anti-proton. Now, a detail is that the protons are much more complicated than just having 3 quarks or 3 anti-quarks. They're a soup of quarks and gluons and anti-quarks and so on. Well, at the LHC, unfortunately, your anti-quark is probably going to have to come out of that complicated soup of the C quarks and anti-quarks and gluons. So that's one other difference.
Yeah, so it's not always a case of more energy, more luminosity is good. Sometimes it kind of works against you. So once we have this set of clean W boson decays, we're pretty sure that they're W bosons. We're pretty sure that this is the decay that's happening. How do we go from there to calculating, or at least inferring, the mass of the W? Because usually what I'm familiar with working in the past at LHC is doing a kind of direct reconstruction where the Z decays to a positron and electron. You can take its momentum, its mass, you can reconstruct back, and you can directly recreate the mass of the Z boson, for example. You get these nice sort of plots. Here you have a sort of neutrino that disappears, and you have an electron. So it's hard to do that sort of direct reconstruction. How do we get to an idea of what the mass of the W is, given the data that we see in these Ws that we've collected?
So your figure of the Z boson mass distribution with that peak is amusing, because if you were to ask probably any student that I supervise, undergraduate project students and summer students and PhD students, what was the first exercise Mika gave you? They'd probably. I have a secret file of Z event, candidate Z events in real data with the momenta of the and directions of the mu plus and mu minus, and I asked them to make this plot. So yeah.
I was just like, what's the cleanest direct decay I can think of? I was like, yeah, Z probably a pretty good one for EE. We'll go with that one. So I didn't know about your secret file, but I'm glad it works nicely.
That's but I didn't actually invent that training exercise. It was exactly the same training exercise that my PhD supervisor Terry Wyatt in Manchester gave me in 2007 or 8 or whenever it was. So anyway, it suggests that it's not super difficult to do that. But with the W, the problem is that you only see half of the decay. Now that's not doesn't quite give the full answer, because actually the problem is that you only see half of the decay, and the W has some energy beyond just its mass.
Yeah.
If the W or Z or anything else was at rest and it decayed into two particles like we have here, you don't need to see the whole decay, because the mass of the decaying particle ends up in the energy of its decay products.
Yeah.
And so if there are two decay products, then they get half each.
Yeah.
So long as you see one and you measure its energy, I might start mixing up energy and momentum. They're very high energy things of light particles. There, we sort of
we use them sort of interchangeably. Yeah.
You could just measure the energy of the electron and multiply it by 2, and that's the mass of the parent. The problem is that the energy of the electron isn't just half the mass of the W. It gets some energy from the momentum or energy of the W had in the first place.
Yeah.
So that's actually why that problem applies to the Z as well.
Yeah.
But the way that you get around that is the plot that you were just showing. That's the invariant mass. So that there we've basically worked out. We've worked out essentially what would be the sum of the energies of the two children of the decay if it was at rest. That's essentially what it's doing. The problem for the W is that you have no way of doing that, because you say, well, I just see one muon and I have no idea what momentum its parent had.
Where's the neutrino gone? Yeah.
So you have no choice but to essentially model how much energy it got from the W. So one way to slightly improve this situation is to not use just the energy, but to use the component of the energy or momentum that's away from the beam direction, because and that's just because the W and Z bosons don't tend to have such a high energy in that direction. That's all it is. Whereas along the beams, because you have at the tevatron, you have one TV colliding, producing something with 20 times less energy. There's a hell of a lot of energy for that to sort of decide to boost along. So we try to get away from that, which is what the variables on the x-axis on this plot are trying to do.
So what we're sort of seeing here for the people who are sort of watching is these are plots. So there's a red line, and then there's the data, which is the blue point. So the red line is sort of or is the red line the fit? I'm not sure which one. There's a model and a fit, isn't there? Is there so best fit is just histogram, data points, background, shaded region. Right. So what we try to do is we have a model of all the physics that we understand from the standard model, and we try to predict the momentum and the energy of those products that come out from the W that we would expect to see, right? So we'd expect this many in this range of momentum, this many in this range, if the physics that we understand from the standard model holds up. And then we sort of one of the sort of floating parameters in that model is the mass of the W, which is sort of the bucket of energy that we can throw at this problem. And then we sort of fit this model and try and pick the best mass of the W, which gives us the distributions, the kinematic distributions here that we see. Is that fair?
Yeah, it's essentially the maybe if we look at the second row, I think that's the charge lepton PT.
Yeah,
that's the simplest of these rows, and the left and right are electrons and muons. But if we just look at one of them, that's exactly what I was just talking about, the transverse momentum of the lepton, and you can see that there's something that kind of looks like a peak, but it's not really a peak, and it's a bit asymmetric.
Yeah.
But either way, if you look at the x-axis, the sort of peaky region is at about 40 GeV, which is half the W mass.
Yeah.
So that's basically saying that a lot of the time, this this component of the energy does as I was not explaining in this naive picture, take away about half of the W mass. So the W mass is about 80 GeV. You're absolutely right that the way the measurement is done is that so there are a lot of data points. It's even so many it's hard to see, but but I think it's now I forget whether it's the red is the data points or the but either way,
they're so close together it doesn't really matter when we're making this discussion. But yes, I think that I think the blue is the data and the red is the model, I think.
But there will be different model templates with different W mass hypotheses, and they would basically have this, on the right hand side of the peak, this sort of falling edge would just be shifted left or right depending on whether you have a higher or lower mass hypothesis, and you see which one fits best. And you do a bit of statistics to sort of actually work out a real minimum and uncertainties, and that's how it's done. So the final fit is actually is relatively simple. It's just the amount of detail that goes into getting a template for a given hypothesis.
Yes. So if we talk about some of those templates, so those templates have to sort of account for the decays of these particles, so the couplings. They have to take account of, for example, synchrotron losses from charged particles before they hit your detector. So do they have the right momentum that you expected? They have to take into account the fact that the protons or the antiprotons are really bags of quarks and gluons, right? So they might not be hitting with exactly the energy that you think because they're jiggling around inside. Things that go into this model, that there's so many potential areas where there can be a slight error which has a knock-on effect on the potential W boson mass that you get from your fitted template.
Yeah, I mean, exactly. The problem is that this distribution that we're looking at has a tiny sensitivity to the W mass. If we change the W mass by even 10 times more than the final uncertainty in this measurement, we wouldn't be able to see it on the, we really zoomed in, and so, or you'd have to plot the ratio or something. Whereas this distribution is hugely sensitive to so many modeling details, and you can broadly categorize it into three problems. One, which is relatively straightforward, I think, is the background, which is this grey bit. We can probably say that's reasonably easy to control.
So just for people who are sort of listening to the background might be things like we thought we were seeing a neutrino and electron decay from the W, but it was really a tau and a tau neutrino decay that we misidentified. So there's certain other decays that can happen that we might misidentify as a W decay incorrectly, and they can have a slight impact on the statistics that we see. So that's what we call sort of background.
Yeah, I think a fun fact about actually the background in this plot, which is actually, it was at the 5-10% level. That's actually that's actually from Z boson decays to 2 muons. So normally you get rid of those by just saying I want events where I just see one muon, and I see one and no more, and I don't see any others. But the CDF detector actually can't see muons everywhere. So a lot of the time there's a Z boson and it produces 2 muons, and it looks just like a W event, and they have no idea that there was a second muon because
it went along the beam pipe or something, or somewhere that wasn't. That makes sense. But
okay, let's see. It's not the biggest problem. But the other two are basically come down to modeling essentially the extra energy of the W boson. How much does it get in the direction that actually contributes to this transverse momentum? That's probably the single most important detail here. How much energy it gets along the beam direction, and that relates to what you were saying about the fraction of the energy that the quarks and antiquarks have of providing protons, antiprotons. And then the other part is, of course, nature will produce a W boson that then decays to a muon with a particular direction and energy, but the detector won't count all of them, and because it has inefficiencies, and there are dead bits of the detector, and so on. That's part. These are hugely complicated detectors that that all has to be modelled. But also the momentum isn't measured. It isn't measured perfectly because there's only a finite resolution. So all of this has to be modelled as well.
Do you know your magnetic field perfectly? Do you know exactly the positions of all the pixels you use to get the curvatures of the tracks and all these kind of things? So that goes into a sort of bin of understanding your detector really well as well, right? So backgrounds, model uncertainties, and then sort of understanding detector resolution as well is a really big thing, because essentially what you see in your detector is a sort of convolution of what actually happened, these real kinematic distributions in the real world convolved with some sort of detector response. So we have to sort of understand that as well. So there's those three bins of sort of problems that we have to overcome.
Yeah, that's exactly it, and that it is unimaginably challenging. There's so many details that matter.
I think we've got this grey box that shows, I think, about the top 10 sources of uncertainty in this result, and some of them we talked about, the energy scale there, the recoil energy resolution. Then you've got the things from the model. Then you've got the parton distributions, which are the jiggling around quarks and gluons. You've got the QED radiation, so radiation that comes off your charged particle before it even hits your detector. So did that disappear and we never saw it? Incredibly large amount of potential uncertainties, and I think this is the top 10. So I think you said there was 50 pages of additional expert material that goes with this paper to delve into some more of the uncertainties and how they got around them as well. Incredibly intricate measurement.
Yeah, I mean, exactly. This, every detail in the model that really matters, and where we don't, where we can't model that detail perfectly, it has to carry an associated systematic uncertainty, and so that's what appears here. Fortunately, the largest, I should say that the largest number on this table, other than the total, is the statistics. That part, fortunately, is relatively straightforward to assess. That's but all of these, but actually, if you add up all of these other sources, then they're comparable. And I mean, it's extremely difficult to control all of these, and it is arguably difficult to really know that you know that the uncertainties really mean what we usually mean by uncertainties, which is that we have a 68% confidence that the true value lies in the range of the central value plus or minus these uncertainties.
And like you said, even though this W boson statistics one is we know how to deal with, just take more data. There's no point if you can't get these systematics below that level, because they're going to start to dominate your uncertainty on your measurement anyway. So understanding your detector, understanding all of these inputs becomes even more important when we've got the statistics down to a similar level, right?
Yeah, I think in some sense that's what defines an analysis as difficult, is when you have to work really hard to get the systematic uncertainties down at or below the level of your statistical uncertainties, because most of the time statistical uncertainties are, we learned how to deal with them in our lots of first year of undergraduate, and often we don't need to use anything more complicated than that, and it's quite straightforward. And we understand exactly what that means. But the systematic uncertainties are uncomfortable and difficult, because it's really hard to know if they're if they really if they give the correct coverage.
Makes sense. So we have to address the delicately, of course, but we have to address the sort of elephant in the room. So this was a plot that former colleague of mine and still a colleague of yours, Will Barter, made, which has been upgraded for an official LHCb plot, which shows that there is quite a strong tension between the Tevatron results here, the CDF result down here at the bottom, and results of the W boson mass from other experiments. So we see LHCb, which is obviously our bias towards Atlas, LEP, D0 in the past. What are we to make of this discrepancy? Because obviously there's been a lot of talk about this in the community. Some people, think maybe that there's an error that's happened in this CDF measurement. Although, we're not trying to say there's any slight or anything wrong has been done, but some people are skeptical of this result. What are we to make of this tension between these different experiments? Because it looks like, on the one hand, the sort of four above quite strongly agree with the standard model and with each other, and then this one is a little bit of an outlier.
You remember it. You like me, you may remember from undergraduate lectures on analysis and statistics. We're drummed in that one standard deviation is 68% and two standard deviation 95. You just remember those numbers off the top of your head. I had to just calculate before. 4 sigma corresponds to there's a 99.99 it's a 1 in 10 to the 4 chance that's a
mistake or a chance occurrence rather than a real result, basically.
Exactly. So it's very unlikely. What does I should also add that we could say, well, I don't know. Well, let's just sort of average everyone together anyway, this exercise has been done, and you're still somewhat discrepant with the standard model. However, by the time you're averaging a set of results that are in huge internal tension, I would claim we have no understanding anymore of really what talking about an uncertainty is very naive, because it's because the uncertainty just representing an uncertainty by one number is approximating you're approximating a distribution of confidence by one number. I think once you're averaging results that are in great tension, you can specify one part of that the width of one part of that distribution by one number. But I don't think we understand the tails anymore.
So the mean is, I mean, people will know this from their GCSE statistics, I guess, or their A-level statistics. The mean can be dragged up by an outlier like this. So if you were to average all of these together, or weighted average them all together, the result is going to be pulled to the right. And if we do that sort of naively, there's going to be some tension with the standard model. And it seems to be that the W boson mass is significantly above the standard model. However, should we be doing that, given that this one is an outlier relative to the other four? Really, our first port of call is to understand why this is so different to the other four. Is that a fair assessment of what you were driving at?
Exactly, and I can say actually, where would that average fit? I don't have the precise number, but I know that the average of the other results is a bit less precise than the CDF result, but it's, it's comparable, which basically means that the average of all of them would sit somewhere, in between.
So like in here somewhere, yeah.
Yeah. So anyway, we need to understand this discrepancy, but it's going to take time. What would probably help the most is, of course, to have new measurements from the LHC experiments. So Atlas and LHCb are here. We certainly expect results from the CMS experiment in due course, and that will certainly help to clarify the picture.
Any idea on timescales for any of those updated measurements, or the first one there in terms of CMS?
Well, I mean, the first thing to say is that if the fact that the W boson mass measurement is difficult is that's not changed.
Yeah.
It's what sort of broadened this the space a bit compared to the Tevatron measurements is, the Tevatron measurements had traditionally just been working to keep, as we were just discussing, keep the systematic uncertainties at or below the systematic uncertainties, and they've done a brilliant job in keeping that going up to now. But so that meant that you would say that they're in the statistics limited regime. It's obvious what they needed to do all along, which was just keep analysing the data as they were coming in.
But if we look at Atlas, the systematics are a lot wider than the stats here, right? So I guess this is what you're sort of driving at.
Exactly. So for particularly for Atlas and CMS, it's a bit less clear. What is the they have the experiments have loads of statistics. It's a bit less clear exactly what's the best strategy to get the best W mass measurements. So one interesting idea that's been floated around for a few years is to try to take special runs at both lower energy and lower instantaneous luminosities. But there are other voices that would argue that we'll come up with other ideas to try to use all of the available statistics and so on.
Yeah.
So somehow the space of possible directions on how to do the measurements is a bit broader.
So do we want to make things a little bit cleaner and easier to understand but have lower statistics, or do we want things a little bit messier but we have much higher statistics? And how do we deal with the associated systematics for both of those approaches is a matter of shall we say robust discussion, sounds like.
Until this CDF result came out, I would have said that now it's still really the LHC as a scientific facility is still somewhat in it's sort of just reaching maturity, and we should be trying different ideas and approaches to the problem, and ultimately building towards the highest possible precision that we can get on something like this, and all other possible measurements with this facility. I've really been encouraged by different ideas on just the W boson mass measurement. Now probably there is more of an emphasis on in the somewhat shorter term, perhaps taking a more conventional approach to produce some measurements to perhaps more incrementally improve the precision, and in the case of the CMS experiment to produce their first measurements. I should say that the fact that LHCb has a measurement at all was that was not something that was really that wasn't on the physics program of LHCb until a few years ago. So the fact that could be done at all was also that was a sort of an interesting surprise.
Yeah, I'm always happy to flag up excellent LHCb sites. So yes, it sounds like going forward we're going to have to wait for more measurements to clarify this. There's robust discussion as to how we should deal with this disparate measurement, but as you say, it does seem like we're going to have to get more results, updated results. The first one from CMS, to try and shed a little bit more light on exactly what's going on here, because it's not entirely clear at the moment, which might not be a perfectly satisfactory answer for some people, but unfortunately that's the way it is in science. Sometimes we need to do a bit more work to understand what's going on. I guess the final question I had sort of about this, and maybe this might be a bit outside your wheelhouse, but I'm sure you know plenty about it anyway, is more on the theoretical side. If this result holds up, let's say that this is entirely correct measurement of the W boson mass from CDF, do we have any insight into what potentially could be causing this, or what new physics might be at play, or is this a job for the theorists? Because I'm sure they've gone into overdrive, and we'll be seeing a lot of papers on arXiv soon of ideas as to new scalar fields and new particles and such, which might solve this problem if it is indeed real.
Well, there's certainly plenty of material that's appeared in the literature in the last 2 weeks or so, what we colloquially refer to as ambulance chasing. But without going into specifics of specific models, we discussed at the beginning how the W and Z boson get their masses in a very almost the same way, just slightly differing in the details of which couplings are involved. But it's essentially some fraction of the energy of the Higgs field. But what if there is, for example, another Higgs field, or a more complicated Higgs sector, and it's not too difficult to come up with scenarios in which one of the other Higgs fields contributes to the mass of the W and not the Z, or vice versa. You have to, of course, ask the theorists for a perfectly accurate description. Yeah. But it's something along those lines. And or there can be new fermions that are contributing to the masses and couplings of the gauge bosons and so on. But these are the types of ideas. But the main thing is it's all beyond standard model. Yeah, the holy grail of our field.
And I think this is the major thing, isn't it? If this W boson is so discrepant, it's a crack in the standard model. It's something that we don't anticipate. So it could potentially give us some ideas and give theorists some ideas as to how to raise hypotheses as to where we should be looking next for new physics. And therefore that feeds into the experimental sides of what experiments we should be doing, what machines we should be creating and such. It's really trying to find cracks in that standard model, isn't it? And show us where to sort of go next. I guess why people are so excited about this result potentially being accurate.
Yeah, I think so. Though, I will.
We don't want to get ahead of ourselves. I'm just. I
think. I think. Look, I think that this has brought to light the interest in this type of measurement, but we're still some way off understanding this 4 standard deviation discrepancy between the experiments before we get too excited about any beyond standard model claims.
I think that's very fair, and that's the correct scientific answer. Mika, I've had a great time discussing it with you. It's been great to get back in contact as well, because we worked on LHCb together in sort of 2011 to 2013 time. So it's been very good to touch base and learn more about this amazing measurement and very fascinating results. So thank you so much for taking the time to have a chat today. I really appreciate it.
Yeah, it's been a great pleasure. Thanks a lot.
Always a pleasure. Is there anywhere where we should point people if they want to know more about what's going on with this measurement, keep up with the details of any updates? Would you suggest anyone go to any particular place to keep up with this?
Yeah, so the LHCb experiment pages where we report new results.
Yeah, it's always very well maintained. I'll make sure that that's in the description, and everyone should head there because
we recently upgraded even.
Exactly, because LHCb is the best experiment, as we know. And there's a few just before we finish, isn't there? There's been, again, not proven yet, but some very interesting potential signals coming out of LHCb, thinking about things like lepton universality and such. LHCb seems to be very much the place to be for interesting new signals. Is that fair?
Yeah, I completely agree. Yes, there are indeed some interesting. There's an interesting pattern of anomalies in lepton universality observables.
Excellent. We will. I will make sure all those links are down in the description. Mika, thank you so much again for taking the time out of your busy day to have a chat with me, and hopefully when we get a little bit more understanding of this and get some new results in, we can have another friendly chat.
Yeah, look forward to it. Thanks.
Absolute pleasure, buddy. Take care. We'll talk to you again soon. Bye now.
Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.